Assalamualaikum and welcome. Today we will be presenting KMG10003 Basic Physics Laboratory 1 Vector and Scalar. A lecture by Associate Professor Dr. Dewi Surani Cik Halim and Associate Professor Dr. Nuraniza Saud. Before I begin, let me introduce myself. My name is Nur Afila binti Khairul Niza and my matric number is 2516048449.
Okay, my name is Muhammad Nazir bin Muhammad Nazruddin. My matric number is 2516048445.
My name is Tengku Nonoha binti Tengku Nazmiwandi and my matrix number is 2516044743.
The objective from this lab is first, to differentiate between scalars and vectors quantities, and the second objective is to determine the resultant of two vectors using a fourth table vector. Next, we move to the introduction. In this section, I will introduce you the two types of physical quantities, which is scalars and vector quantities. Scalar quantity only have magnitude, for example, speed, temperature, mass, and distance, while vector quantities have both magnitude and direction, for example, velocity, force, and weight. So, in short, scalar tell us how much, while vector tell us how much and in which direction. Next, we are going to learn about resultant vectors and equilibrium condition. A resultant vector is the single vector that represents the combined effect of two or more vectors. In simple terms, if multiple forces act on the object, the resultant vector shows their overall effect. That is equilibrium condition, a state where an object is either at rest or moving at a constant velocity, meaning there is no acceleration. Next, we move to the vector addition method. The first vector addition method is tail-to-tail method. Tail-to-tail method is when the head of the first vector A is connected to the tail of the second vector B. The resultant of vector A plus B is formed by connecting the tail of the first vector to the head of the second vector. The second vector addition method is parallelogram method. Parallelogram method is when the both vectors start from the same initial point. The diagonal of the parallelogram is the resultant of vector A plus B. First, we resolve each vector into its horizontal and vertical part. Next, we add all the x components to find the resultant x value, and we add all the y components to get the resultant of y value. Using the theorem Pythagoras, we calculate the magnitude of the resultant vector. R equal to the square root of the sum of the total fx and total fy. To find the direction, we use the formula theta equals to inverse tangent of fy over fx.
And then, we move to the experimental materials that we need. We need force table with pulleys, ring and central pin, strings, weight hangers and slot weights, protractor scale, and the last one is ruler. The experimental procedure that we do is, firstly, the force table was leveled and the pulley were checked to move freely. Then, 3 strings with no mass were attached to the central ring and passed over the pulleys. Next, the angles and mass were adjusted until the ring stayed at the center, indicating the equilibrium. Of force magnitude and angles were recorded from the 0-degree reference line, and the resultant of two forces was calculated and compared with the third balancing force. Then, the procedure was repeated with different sets of force magnitude and angles. Lastly, vectors were drawn graphically using a suitable scale to determine the resultant. So the experimental, graphical, and analytical results were compared.
Okay, this is my part. The table show the force table measurement. This is the first table that we record. As you can see, for record 1, we put a 3 magnitude and 45 degree angle. And for force 2, we put a 2 magnitude and 13 degree angle. Each force has been calculated and will be the reference axis.
The slide shows the calculation steps for resolving force 1 and force 2 into their fx and fy components. For F1, we get F1x equal to 2.12 Newton and F1y equal to 2.12 Newton. For F2, we get F2x equal to 1.73 Newton and F2y equal to 1 Newton. To find the calculated resultant, we add both x components, F1x plus F2x equal to 3.85 Newton, and both y components, F1y plus F2y equal to 3.12 Newton. Next, we substitute this value into the resultant formula and we obtain R equal to 4.96 Newton. The angle calculated from tan -1, Fy over Fx is 39 degree. Referring back to table 1, our experimental readings show a resultant of 5.5 Newton and an angle of 38 degree. So the percentage difference between the calculated and experimental value is approximately 10.9%. The diagram shows the table 1 vector diagram for F1 and F2.
After that, this is a second table that we record. The table 1 and 2, we put the different force and angle. The force 1, we put 1 magnitude, and force 2, we put a 2 magnitude. For the angle, we put a 20 for the force 1 and a 14 for the force 2. Each force has been calculated to will be the reference axis.
This slide shows the calculation for table 1. For force 1, with a magnitude of 1 Newton at 20 degree, we get F1x equal to 0.94 Newton. F1y equal to 0.34 Newton. For force 2 with a magnitude of 2 Newton at 40 degree, the components are F2x equal to 3.06 Newton, F2y equal to 2.57 Newton. To find the calculated resultant, we add both x component, F1x plus F2x equal to 4 Newton, and both y component, F1y plus F2y equal to 2.91 Newton. Next, we substitute this value into a resultant formula, and the calculated R is 4.95 Newton. The angle obtained from tan -1 Fy over Fx is 36 degree. Referring back to table 2, our experimental value for the resultant is 5.4 Newton, with an experimental angle is 30 degree.
Okay, for the part discussion about the relationship between resultant and balancing force. It is the resultant force is the combined effect of all force acting on the ring, while the balancing force is the force needed to oppose the resultant and bring the system into equilibrium. Ideally, both forces should have the same magnitude but act in opposite direction. In this experiment, the balancing force measure was close to the calculated resultant, showing that the system followed the principle of vector addition. Next, for the discussion number 2, it is a accuracy of a result. The percentage difference between the calculated and experimental resultant were 10.9% for the table 1 and 9.1% for the table 2. This value show reasonable accuracy because minor force table experimental commonly involve small deviation. Overall, the results were close enough to the theoretical value to confirm the effectiveness of method used.
The common source of error that we find in our experiment is the friction in the pulleys reduced the actual tension in the string, affecting the equilibrium. Small inaccuracies in weight measurement may also change the force value. Angle reading errors such as parallax and misalignment of the string can alter the direction of the applied force. These limitations explain why the experimental value differs slightly from the calculation. Scalar quantities have magnitude only, such as mass, temperature, and time. Vector quantities have both magnitude and direction, such as force, velocity, and displacement. In this experimental, force is treated as a vector, so it must be resolved into horizontal and vertical components before being added. The distinction is important because only vectors can represent both size and direction of physical effects.
Then conclusion that we can summarize for the experiment. This experiment has successfully accomplished its aim of differentiating scalar and vector quantities and ascertaining the resultant force for the two force vector. The finding indicated that there is a favorable concordance between the resultant force value acquired analytically are calculated and experiment, thereby validating the accuracy of the vector component method. Moreover, the principle of the force equilibrium was substantiated when the net force on the system was zero. In essence, the component method is a efficacious and dependable instrument in scrutinizing for vector force. That's all from us. Thank you.